Okay. So today, hands-on quantum computing. Now, what is the plan for today? I split this presentation in 3 parts. In first part, I will give you a brief overview of quantum computing. I assume that people who are attending this conference are mostly not familiar with quantum computing, at least from my previous experience from data science conferences. So this is why I decided instead to jump directly to programming quantum computer. I decided to give some introduction. I want to tell you what is quantum computing, why do we need quantum computing, where are we now, what quantum computers can do today, what quantum computers cannot do, what we can expect. So this is first part. In second part, we will have a quick introduction to quantum programming, because again, I guess that people are not familiar with quantum programming. And I want to show you, at least to give you an idea what we are dealing with when programming with quantum computer, how it looks like, how quantum computer works from software perspective. So this is one. This is part 2. And in part 3, we will have hands-on coding sessions. So I will make a simple quantum program from 0, and we will see we will execute program, see some results, and that's it. So, and of course, in part 4, we will have Q&A session. You can ask me anything. Also, during the presentation, you can ask anything, put into QA or into chat your questions, and I will try, between sessions, I will try to answer your questions. If you have some questions, feel free to ask. I'm happy to answer. And so this is the plan, and let's go. Now, part 1 about quantum computing. First of all, what is the motivation for quantum computing, or not only quantum computing, but unconventional computing? Today, we have ever-increasing demand for information processing. And especially last few years with artificial intelligence boom, let's say, we have increasing demand for information processing. A lot of energy is spent on processing data. Data centers are full, so one of the motivation is that we have more and more data and more and more data to process. And another even more important motivation is that we need in order to progress, to move forward in every industry, in every science and every industry, we have problems that are hard to solve, or unsolvable problems with classical digital computers. So motivation is to solve complex problems that are and some problems that will stay forever inaccessible to classical digital computers, or to perform what digital computers can do today, to perform faster or with lower cost, or with less energy consumption, or with better quality or precision. This is motivation. And in this graph, you can see green lines are easy, problems easy to solve. So this is size of the problem. At x-axis is size of the problem, and at y-axis is time required to calculate. And you can see that these red lines are problems that are very hard to solve. Those problems are unreachable with larger input size, with larger size of the problem. Problems of this complexity, like factorial complexity and exponential complexity, is very hard to solve on classical digital computers. And for that reason, we are thinking, and there is research in different directions, how to make unconventional computer, which is not classical digital computer, but some computer which use different technology to perform calculation with hope that we will reach and solve these hard computational problems. And now one of unconventional approaches is quantum computing. So let me continue. So quantum computing. So what is quantum computing? Quantum computing is use of quantum mechanics to solve hard computational problems. So this is quantum computing approach, is to use laws of physics, which is how to say, on which universe is based, to perform computation. Now, on this picture, I can show you. You can see in this picture. You can see at the left side, this red thing is Google's superconducting quantum computer. It's in maintenance at the moment in this picture. But anyway, so this is quantum computer. This is it is superconducting. It's running on near 0 Kelvin temperature, and at the right picture there is a IonQ quantum computer, which is ion trap or ionic quantum computer, which is using trapped ions or atoms to perform calculation. People usually, I already had situations that people ask me, do quantum computers really exist? And quantum computers do exist, and quantum computers are available in the cloud. I will show you later. So quantum computers are reality, and we have quantum computers in, I mean, all over the world at the moment. But quantum computers are still experimental, not yet commercial. But we will talk about that later. So let's continue. Now let's see what is the potential of quantum computing. So what potential quantum computing has? Now this diagram is maybe nice way to show what is the potential of quantum computing. We can see different classes of problems, or not classes, but different problems with different complexities. And at the left side, we have most complex, at least most complex on this picture, exponential problems. And at the right side, there are least complex problems, or problems easiest to solve. Now you can see that some quantum algorithms, like this Deutsch-Dosa problem, which is extreme example, can perform some computation, which is on classical computer has exponential complexity. It can perform in constant complexity on quantum computer. This is most extreme example, but there are other examples also very important. We have like Simon's algorithm, Grover's Shor, quantum Fourier transform, and so on. And you can see that this is something that classical computer cannot do, and most likely will never be able to do, because currently, because a lot of research is already spent into classical digital computing. If some problem is exponential, there is a small chance that somebody will invent algorithm which will perform in linear time or in constant time, something that is exponential. Simply, there is people are trying for almost 100 years to do this, and so this is very major. So classical algorithm and computer science is very major branch of science, and this is where we are. So this is what quantum computing possibly can offer. But I will tell you that simply for practical size of the problems, we are not there yet. We can perform only small computations. I will tell you later about that and how far we went. But this is theoretical potential. Now let's continue. Now, because we are moving frontiers or how to say limits of computation, the impact could be huge. And impact can be on every industry. I put some examples on this slide. You can see healthcare, for example, where quantum computers can help find new drugs for deadly diseases by calculating molecules which can interact with, for example, with proteins in human body and make some cures. Personalized medicine for cures for diseases that are different for every person. In chemistry, new materials, new catalysts for chemical reactions. In energy, new energy sources, better batteries for electric vehicles, and so on. So impact could be huge, and I guess that you are coming from computer science, all of you, I guess, and you understand how big implications can this have on humankind, if I can say, and because that industry is already preparing. So I assembled a small list of companies who are already experimenting, and trying to use quantum computing in their operations. Still, they are not using quantum computing in operations, but they are experimenting and assessing what quantum computers will be able to do for their business. And here you can see for few industries, again, only few, not a complete list. You can see from each industry, I put 3 or 5 or 4 companies, and you can see that these logos are familiar. These are mostly large companies who have budget for let's say unconventional computing, and they are already playing with it. Some companies have internal quantum team. Some companies are using like startups or big techs to do research for them. Anyway, industry is preparing. Now we have customers and we have providers, and providers are both big tech and startups. So now you can see in this first row, you can see Google, IBM, AWS, and Microsoft. Apple, from big techs, Apple is not in the list because Apple is not yet in quantum computing game, as far as I know. But Google, IBM, AWS, and Microsoft, they are already providing both hardware and software for quantum computing. And there are also other, like Atos is European, let's say big tech, European big tech, if I can say. Then we have quantum startups like D-Wave, Canadian, Rigetti, Quantinuum, IonQ. Those are publicly traded startups. So these startups became publicly traded companies recently. And we have smaller startups. Of course, the list is not full. This is not a complete list. Of course, there are many companies and many startups who are operating in quantum computing space. One of the startups is Quantastica, my startup, registered in Helsinki, in Finland. And so just for you to understand that quantum computing has both customers and providers. So quantum computing is a reality. Quantum computers do exist, and but there is no quantum advantage yet. So currently, at this moment, quantum computer cannot perform faster or with lower cost, with less energy consumption, and also not with better quality and precision. This is so quantum computing. This is why quantum computing is still experimental. It's still not yet used in operations. So quantum computing is simply emerging technology, which is not yet used commercially. And why is that? Part of the problem is quantum hardware, because it's very hard to how to say, to control quantum mechanical effects, quantum mechanical phenomena. It's very hard to precisely control quantum mechanical effects, and quantum computers are machines, advanced machines, maybe most advanced machines that human hand ever made, and and hardware is imperfect. We have noise. Noise is maybe the biggest problem today, because simply quantum computer doesn't return exact data. It returns some randomized outputs, which is problem. Now we have qubit. Qubit is basic unit of quantum computation, and we have number of qubits is in some technologies problem. There are different technologies of quantum computers, so there is not only in this picture is superconducting quantum computer, but there are also ionic, photonic, and multiple different kinds of quantum computers. So different technologies have different problems and pros and cons. Qubit coherence, because quantum computers simply spontaneously lose the how to say state, and qubit connectivity, gate fidelity, and so on. So there are hardware problems, but today we will not talk too much about hardware. We will talk more about software. So let's see. So part of the problem is hardware. Part of the problem. So why quantum computers are not commercial yet, and why quantum computers are not yet better than classical computers? One part of that problem is hardware, but other part of the problem is software or quantum algorithms. Quantum algorithms are very unexplored space. Unlike classical quantum, there is a lot of space for innovation and for improvement, and this is what makes quantum computing so exciting. To be in if you are in quantum computing today, you are directly pushing the technology. How to say, the edge of technology, you are pushing it forward. So you have chance, if you join quantum computing, you have chance to change the world, how to say. And on this picture, you can see few famous scientists like Bell, Shor, Grover, and there are only few quantum algorithms which are promising, which are scalable, which can run on, which are resistant to noise and so on. And if you want to solve some real-world problem on quantum computer, you can use only a small set of algorithms, and this is the problem. And most of these algorithms, most famous algorithms, which I put on this list. This is, of course, not complete list. This is only a few, let's say, most frequently used quantum algorithms. Most of these algorithms are not actually scalable to practical size, useful for industry. So there is a lot of space for improvement, and quantum software is a big, maybe even bigger problem than quantum hardware. Why is that? Because programming quantum computers is much harder. It's much more challenging than classical digital computers. Classical digital computers are relatively intuitive, and quantum physics is, by nature not intuitive for us humans, and we are trying to program quantum mechanics, to automate quantum mechanics, which is very hard. So part of the problem is quantum. Other part of the problem is quantum software. So we have quantum hardware and quantum software, which are currently problems. Now, what we need a winning quantum algorithm. when talking about software, so in hardware there are other problems, but in software we need winning quantum algorithm, which solves some real world problem, something that is useful to people, because there are reports that scientists solved some problem faster than a classical computer, but that problem doesn't have any practical use. This is some which is very good as an example or showcase that which as a proof that quantum computers can do something faster than classical, but that's something that they made is not useful to anyone. Nobody will give you money for that. So in other words, so we need to solve real world problem. We need algorithm which will efficiently utilize quantum hardware, which doesn't need a lot of qubits, doesn't need too large quantum computer. Algorithm which is robust to noise and errors, problem that is scalable to practical problem sizes. So some quantum algorithms can work only in small size, but when you try to scale it to perform bigger input size, to process bigger input size, it simply is not scalable because some problems with quantum hardware and noise and decomposition and so on. And it's important to have quantum algorithms which are implementable on available quantum hardware. So this is what we need. This is kind of maybe not holy grail, but we really need better quantum algorithms, and a lot of research is put into that direction. And I will tell you where are we now. This is not impressive. Contrary to what you read on internet, on some popular blog posts that quantum computer can break encryptions and so on, we are far from that. At the moment, and this is what quantum computers can do. So I put three famous, or how to say, problems that people mostly are aware of. One of the problem is traveling salesman problem. This is problem of what is the shortest path between multiple points or multiple cities, if you want. And this is problem hard to solve, problem with high complexity. Quantum algorithm, which we have in this case, there are multiple quantum algorithms, but I put quantum approximate optimization algorithm. And this speed up of this algorithm is super polynomial. But problem is that currently the state of the art quantum computer can solve only 5-city problem. So this is traveling salesman problem with only 5 points or 5 cities. This is small. You can do that by hand. You don't even need a pen and paper, not to mention quantum computer or quantum computer. But the potential is high. Why only 5 cities? Because noise, because hardware is noisy, because this algorithm is not optimal. We need better algorithm, and so on. So, but this is not impressive. But the field is advancing every day and every month, and maybe on next presentation I will have something better to show you. But currently, this is traveling salesman problem. Second, integer factorization. Integer factorization is important for internet security, because internet security depends on factorization, integer factorization problem, which is which has high complexity, and it's proven that classical digital computers will never be able to solve to factor large integer in practical time. And this is why security, many encryption algorithms are based on this on integer factorization. Now, quantum algorithm can perform that faster, and theoretically can perform it better and faster than classical digital computers. And again, in this case, speed up is super polynomial. That means if quantum computer could do that, it will break some encryption in relatively short time, in practical time. But largest number factored with quantum computer, with universal superconducting quantum computer using Shor's algorithm, is 21. So quantum computer can tell you that 21 is equal to 3 times 7. This is what quantum computer can do. There are also specialized quantum machines which are made only for factoring numbers or only for specific problems, not only factoring numbers. For example, for this for this traveling system problem, for combinatorial optimization problems, there are specialized machines which can perform more. But here I'm talking about universal quantum computers. And even those machines, those specialized machines, are not very impressive. So they are not even close to solving practical problems, problems of practical size, which are unreachable for digital computers. So this is where we are with integer factorization. And with molecule simulation, it's very hard to actually find, because there are multiple. I was searching for many papers, and in different papers, we have different results, and it's hard to say which is the largest molecule simulated on a quantum computer. But I put this fluoromethane molecule here, but mostly the largest molecule is 5-atom molecule. So quantum computer can simulate minimal energy of molecular bond of 5-atom molecules, which are relatively small molecules, and not all molecules, not all 5-atom molecules. And if you compare that with molecules in human body, which are large molecules, proteins, for example, are very large molecules, DNA, not to mention DNA. So we are very far from making, personalized medicine and so on the computer. But again, to say that this field is advancing every day, and we have better and better, larger and larger, and more precise quantum computers. So, so who knows? Quickly we will move much closer to something that is of practical use. So this is about this is overview of quantum computing. Now I guess that you have some view on what is quantum computing. Of course, you read everywhere about quantum computing, but this is what quantum computing can do. Now let's talk about introduction. So this part 2 will be introduction into my practical, into third part, practical part. And for that, I wish you to understand how quantum computer looks from software perspective. So I will not talk about quantum physics, and I will not use complex mathematics for this. I will try to use language which is familiar with for people from classical digital computing, and just for you to get idea on how it looks to program quantum computers and what are the problems here. So what problems we have to make quantum algorithm. Now, let's see. First, in this picture, you can see how classical digital computers and quantum computer work together. So CPU and QPU. QPU is quantum processing unit. Now, at the upper part of the screen, we have classical computer. And at the bottom part, there is a quantum computer. Now, in a classical computer, we have some data, some input data, some data that we want to process and to produce output, produce results. This is our goal. Now, for complex problems, we will try to use quantum computer or quantum processing unit. Now, quantum computer has its state. It has quantum state. I will tell you more about this in more details, much more details. But quantum computer always initialize when you turn on quantum computer, which is in ready state for computation. It always initializes in zero state, in state called zero state. And that zero state, and there is no something like input port, so you cannot simply write information into quantum computer like you can do in with classical computer. There is no input port where it will receive information directly, and you cannot write into this zero into this quantum state. You cannot modify it directly. You can only execute program which will change state of a quantum computer. You can think of a quantum computer state. It can be something similar like memory in classical computer. So let's say that this quantum state is actually memory of a quantum computer and quantum program. And in that memory, you cannot write, and also you cannot directly read, which is crazy, you know. But I will explain you later. Now, in order to put information into quantum memory, or into quantum memory is not the good word, into quantum state, to put your input data into quantum state, you need to encode data in a form of a program which will transform your initial state or zero state of a quantum computer into prepared state in which our data will be encoded. So in this middle box here, we have state which has our input data encoded into it, and then main quantum program executes and produces final state. Let me move this Zoom window. Okay, produces final state, which we then can measure. I said that there is no direct read, so we cannot directly write, and also we cannot directly read. We can only sample. I will explain later, but we can measure that final state and decode information out of it to get our output data. So this is how CPU and QPU work together. This is how we will use quantum computers. Now, quantum computers will most likely be in the cloud. Currently, we have quantum computers in the cloud. We don't have quantum computers on our tables yet, or inside our laptops and and cell phones. Not yet, maybe in the future, but currently, the quantum computer is in the cloud. So our classical computer takes input data and code that into quantum program, sends that to quantum computer. It executes program, state preparation program, or how to say, maybe data encoding program and main program, and then we get data out of it. So this is how quantum computer process information. Now let's talk about this state. Let's talk about this state of a quantum computer. This, let's call it memory of a quantum computer. So state vector. So this state of a quantum computer is called state vector, and I gave you some examples here. Let's see this leftmost. We said that qubit is basic unit of quantum computation, and qubit can be elementary particle, for example, photon, or ion, which is actually atom, with extra or less electrons, or can be other quantum mechanical system, for which we are interested into two possible outcomes from that particle. For example, photon can be horizontally and vertically polarized, and we are interested to measure is it vertically or it is horizontally polarized? So it has two possible outcomes. But elementary particles have also property, or how to say, the elementary particles can be in a superposition of both states. For example, photon can be in a state in which is not horizontal, not vertical, but some mix of both of those states. And we have probability of reading particle, or let's use word qubit. So we have probability of reading qubit when qubit is in that superposition state. We have probability of reading it 0 or 1. So let's say that horizontally polarized photon is 0 and vertically is 1, or I don't know, electron spin up is 0, electron spin down is 1, or something like that. You know, we can attach 0 or 1 to those states. And now when qubit is in superposition, we can read 0 or 1 out of it. So this is all we can read from quantum computing. We can only read bit string, but it has a probability of reading one or another. In this example, this is 50-50 probability. So 50% probability of 0, 50% of 1. But it's not that easy. This probability is actually is something that we, as an observer, we can read by measuring many times. We can read by sampling. We can read we can read this probability distribution. But quantum state is actually a vector of complex numbers. So quantum state is actually a complex number which can be negative, which can have both real and imaginary part, and probability. But this is something that we cannot directly access. We cannot directly write into it. We cannot directly read out of it. But we can only mutate it. So we can change it by executing quantum program. We can change this vector, and which will change probability of reading 0 or 1. This is one qubit. But when we have multiple qubits, for example, this 2 qubit, trick is that qubits, not only that individual qubit have probability of reading 1 or 0, there is also quantum, how to say, phenomenon that qubits can be entangled, or the probability can be in some relation. Like we can put, if we measure 0 from one qubit, if other qubit is entangled, then we will read 0 from another qubit as well. And how qubit this is complex to explain, and it will take a long time. But anyway, so you need to understand that the state of quantum system, of a multi-qubit quantum system, is a vector of complex numbers, which are actually probability amplitudes. They are called probability amplitudes. State vector is usually marked with Greek letter psi, and it's important to understand that n qubit system has 2 on n these amplitudes. Now if we have 272 qubits, then our state vector will have as many elements as number of atoms in the observable universe. So that vector is giant vector. But it's also important to say that this vector is not stored in a quantum computer, we only have particles or qubits. So we only have qubits, and we can manipulate individual qubits. So we can change probability of reading individual qubit, which then affects the entire state. So by modifying individual qubits and entanglement between qubits, so that relation of probability between qubits, by changing that, we are actually changing large, giant vector in case when there are many qubits. So if we have 272 qubit quantum computer, when you modify one qubit, you actually modified vector was, I mean, you are modifying probability of a system whose size can be mathematically how to say, explained or mathematically written as a vector of as many items as number of atoms in the observable universe. So this is the power of quantum computer. The power of quantum computer is lying in that superposition and entanglement. But if I continue talking about that, I will then start talking about quantum physics, and we don't want that, and we don't have time for that. And important to understand is that state of a quantum computer is vector of complex numbers, or we can see it, or we can imagine it as a vector of complex numbers. There is no vector stored inside. There is no memory which is stores all that numbers. It is only mathematical abstraction. So state of a quantum computer is vector of complex numbers. So let's continue. I will show you a few examples. I already told you that zero state, when you turn on a quantum computer, it is initialized into zero state. And what is zero state? Zero state is probability of reading all qubits. In this case, this is 3 qubit state vector, 3 qubit quantum computer, some small, very small quantum computer. We have 100% probability of reading all 3 qubits in state of 0. So we will read 0 from all 3 qubits. And this is zero state. This is initial state. And when we are programming quantum computer, we are always mutating. We start mutating or modifying this vector from this zero state. First element is 1. All other elements are 0. And of course, important to mention is that sum of all probabilities is always 100%, because we will read some of these outcomes. We will always read some of these. So it must be, the total sum must be 100%. It's always 100%. So this vector is actually a unit vector. This is also important to say. So state vector is unit vector in complex vector space or Hilbert space. But let's not talk about physics and mathematics. So now, this is another example. This is hello world of quantum computing. This is Gehazi state, in which all 3 qubits are in equal superposition, and all 3 qubits are maximally entangled. So this is in this state, we will read either all 3 qubits in 0 state or all 3 qubits in state 1. This is and this state is called Gehazi state, and it can have this is often hello world, and I will give you one small example with that state. Anyway, and I also added some random state only to show you that simply this vector can be anything, can have any values, as long as total sum is 1. So this element, absolute value of this element squared is equal to probability. We have rounding here because this is a small number, so it says 0%, it's more than 0. But anyway, so by for example, this 0.577, when you square this number, you will get 0.33. So all elements, absolute values of these complex numbers squared will give us 1 or 100%. This is a state of quantum computer. And when we read from quantum computer, I said that we cannot write into state vector, we can only execute program. I will show you program later. But now when we read from state, we cannot read this vector. This is inaccessible. And this is not engineering problem. So not that we didn't find a way. It's actually the fundamental principle of quantum mechanics. So we will never be able to reach to access these values directly. We can only sample. So when we measure qubit, when we want to read state of, is qubit in state 0 or state 1? So when we read this register of qubits, we can only get this bit string. So we will find qubits in state like 1, 0, 1. And this is what we get. Next time when we execute, we will get 0, 1, 1, like 0, 1, 1. And when we measure, so when we read the state, the qubits, this quantum state is destroyed. So it's said that it collapses. So it loses superposition and entanglement and becomes classical. Behaves, how to say, the state probability behaves classical. So when we read, by reading quantum state, we destroy quantum state, and all we get is a bit string. And I intentionally marked this bit string as an outcome, even if this state is not doesn't have the maximal probability. The biggest probability is actually this 0, 1, 1 state. It has 33% of probability. But of course, when you are running, when you measure, you can even get this result, which has only 1% of probability. So in order to get this probability distribution, you need to repeat experiment many times. So you need to measure 1,000 times, 100,000 times. And then, for example, if you run experiment 100 times, then you will get this element 33 times, this element 29 times, this element 14 times in ideal case, but you need to perform more than 100, experiments to get to reconstruct the probability distribution. Of course, you can indirectly reconstruct this state, this imaginary, how to say, these complex numbers by performing quantum tomography. But this is long story and we will not talk about that. But you can do that indirectly. You cannot directly read these values from quantum computer. You can only read from quantum computer, you can only read one bit string. Now let's go and let's see what is quantum program. Now we start with initial state. So quantum computer is initialized in 0 state, which is in this case, this is 2-qubit quantum computer. I'm using these small vectors because, to fit on the screen, but 2 qubits is not useful. I mean, you cannot perform anything useful with two qubits, but just for clarity, we are using small system of 2 qubits. So both qubits are 0. So when we read state of this quantum computer, we will read this 0, 0 bit string with 100% probability. And now we want to, for example, we want to encode data into our quantum state. To encode data into, and when we encode data into quantum state, we will the quantum state will mutate. So we will again have vector. We will again have unit vector, but only with different probability distribution. So quantum computer is actually mutating state, and this is equivalent as vector matrix multiplication. So state of a quantum computer is a vector, and quantum program can be seen as a matrix. And the result of executing quantum program is actually dot multiplication, so matrix vector dot product, which gives us a new and final state. This is quantum program. So quantum computer cannot do, there are no branching, there is no loops, there is no things like that. Of course, you can do it in high-level programming language, but at the end, it produces quantum program, which then is actually a matrix. So equivalent of a quantum program is matrix. And when dealing with when programming quantum computers, we are actually programming, we are making matrices. So we are dealing with linear algebra, with vectors and matrices. And now this quantum program from this example is some matrix, but quantum computer cannot execute arbitrary matrix. So quantum computer, let me go back one slide. So quantum computer cannot perform any operation, cannot any matrix, how to say, because quantum computer actually has instruction set. And what is instruction set of quantum computer? Instruction set is set of usually only three or four matrices. And in order to perform some computation or to execute some matrix on a quantum computer, we need to decompose that matrix into instruction set of our quantum computer, which adds even more to difficulty and complexity of programming quantum computers. But anyway, let's continue. Don't worry, don't be afraid. So this matrix can be decomposed into three small matrices. I choose this because these matrices are hello world of quantum computing. This is why I choose these two actually matrices plus identity. Now we can execute this Hadamard matrix. So in quantum computing, we have names for matrices. So different matrices have names. And in this case, this is Hadamard. This matrix is called Hadamard. This is identity matrix. Everybody knows for identity matrix. And we have this control NOT or controlled CX gate, which is 4x4 matrix. It affects 2 qubits. And this Hadamard gate affects 1 qubit. And because we need 4x4 matrix, not 2x2, we make a tensor product. This symbol is tensor product. We multiply Hadamard with identity, which result will be 4x4 matrix. And then those two matrices, quantum computer will multiply, how to say, the effect will be when you execute Hadamard and identity and C naught, the effect of execution will be like you multiplied state vector with this matrix. So quantum program is actually set of linear combination of matrices. Now let's continue. Because dealing with matrices is very hard and non-intuitive for us humans, we need a better way to present matrices. And better way or more intuitive way is quantum circuit. So these symbols here at the bottom of the screen is quantum circuit. These horizontal lines are qubits. This is 2 qubit quantum computer, so we have 2 qubits, 2 horizontal lines. We have Hadamard. This box with H is actually this matrix, Hadamard matrix. This identity is not shown in the circuit because identity doesn't change anything. It's only here to multiply to tensor multiply this Hadamard bit to produce 2-qubit matrix or 4x4 matrix. And we have second gate, so we have 2 instructions or gates. So instructions in quantum computers or those matrices are actually called gates in quantum computer. So on this picture we have Hadamard gate and we have C0. So this matrix is presented in a diagram with this symbol. And so this is more intuitive way of dealing with matrices. Now imagine if this matrix is large, like 100,000 by 100,000 elements. This is something that you simply cannot deal with. You cannot look at it, but you can write those matrices as a quantum circuit. Now this quantum circuit is handy for humans, intuitive for humans, but in order to put that into quantum computer, in order to how to say execute this diagram on a quantum computer, you need to write it in the form of program. So there is quantum program, and in this picture I show quantum assembler. This is open chasm, and this is frequently used quantum format for importing and exporting quantum circuits between different quantum programming frameworks. And this is very frequently used language. So I put assembler. I will show you Python later. Anyway, so this quantum assembler, and it's relatively simple. There is only few instructions, and you can see this is header. This is some include some library, and there is quantum register. QReg means quantum register named Q with 2 qubits. So this is quantum register Q with 2 qubits. And then we have classical register. This CReg means classical register. This is classical register, which is with size of 2 bits, classical bits, which will receive or which will store outcome of a quantum computation of measuring a qubit. So this symbol is measurement. It measures qubit and stores 1 or 0 into classical register. In this case, I will show you later. So then we have Hadamard. So this H, this is Hadamard on qubit 0. Hadamard on qubit 0. Control X or control not is CX between qubit 0 and qubit 1. So control X between qubit 0 and qubit 1. This is it. And we have measure, this symbol, qubit 0 into classical register 0, into bit 0. So classical register bit 0 will receive outcome from this first qubit, and second bit of classical register will receive outcome of qubit 1. So this is how you write quantum program. More complicated quantum programs have more instructions, but less or more, this is how quantum program looks like. And let me show you. So this is quantum assembler, but we have also we have Python. And mostly people are programming quantum computers in Python, not in quantum assembler. Quantum assembler is also handy, and also handy for importing and exporting and manipulating with quantum circuits, but people are mostly using Python to write. And there are different frameworks, Python frameworks. Qiskit is most popular. This is IBM's open source quantum programming framework. There is also Google Cirq. So Google Cirq is also very popular quantum programming framework or Python framework. And then there is PyQuil, which is from Rigetti. There is a Q#, not listed here, not written here. Q# is Microsoft's quantum programming language, but this is language, not Python framework. So Microsoft reinvented the wheel. They made a new language for quantum computing. Anyway, let me show you this. This is very similar, like previous example. In previous example, we had this, this program, the same program in Python. We import libraries. We import functions and objects that we need. We make backend because we will execute these programs. So we make backend, and in this case, this is simulator. Backend can be real quantum computer, the name of the real quantum computer, which is sitting in the cloud. And when you execute this program, if you put this here, if you put quantum computer, of course, with some changes in this line, the program will actually execute on a real quantum computer in the cloud. If you have API key, which you get from IBM and so on, but this is how you execute quantum program on quantum computer. So not a big deal. I mean, this is relatively simple. Now we have we create quantum circuit object, which is and we put two registers. We put quantum register of 2 qubits and classical register of two classical bits. We add those registers to quantum circuit, and then we perform our gates. So QC.H, so this means Hadamard gate on qubit 0, CX between qubit 0 and qubit 1, this, and measure. This is very similar to what we had in previous slide. And then we have this execution block. Here we actually execute this quantum circuit. So we execute this quantum circuit. We say on which backend, is it simulator or real quantum computer, and how many shots. So how many times to execute and measure. Because from single execution, we will get only 2 classical bits. And if we are interested into probability distribution, we need to execute many times, and then to statistically get counts or to statistically get probability distribution of outcome from quantum computer. So this is how quantum program looks like, and everything else you see is actually dealing or manipulating with this circuit. So less or more, this is how quantum program looks like. And one additional thing to say, and this is end of second part, before end of the second part, just to say that there are 2 approaches to quantum programming. There is quantum algorithms, which are in entirety executing inside quantum computer. So you take data from classical computer and code data into quantum state, execute quantum program, and then you read data out from quantum state. This is what I show you in my slides. But there is also another approach, which is hybrid quantum classical or so-called variational algorithms, where classical and quantum computer are working together in a loop, and the quantum program is used to perform part of the computation. And in classical computer, we have a classical optimizer, like we have in machine learning applications. And it executes, so quantum program can be parameterized and by changing parameters, which are real numbers. By changing those parameters, we are changing quantum program. We are actually changing the matrix of because quantum program is actually a matrix. And we are executing that matrix, we get the vector, and then with optimizer, we are searching for some minima, which with some calculation with our input data will get us output data. So quantum program is something like let's say like training neural network. So when training the neural network, you are actually modifying parameters with optimizer, and you are modifying this, and this is something similar. So there is two approaches: quantum and hybrid quantum classical, and both have pros and cons. Quantum is hard to encode data into quantum state. Then quantum program is how to make quantum program and how to decode that information from quantum state. So we have some difficulties when program is classical quantum. I mean, when program is only quantum. But when this is hybrid quantum classical, then we have again problem how to make this parameterized circuit to have as less as possible parameters. And because a number of parameters in this setup is when the problem is problem of practical size, not some school example, but a problem of practical size, it has a lot of parameters, large number of parameters, and the objective function is noisy. We have barren plateaus. It's very hard to optimize, and it's challenging to make optimizer which will perform well. So hybrid algorithms have different difficulties. It's much easier to actually make a quantum program itself, because quantum program in this case is not processing our data. Quantum program is processing data. So we need to make smart quantum program which will process our data. But in this case, we are trying to make universal quantum program which will, by updating parameters, will perform any matrix, any how to say to change vectors in a large how to say large space, large Hilbert space. Anyway, so this is quantum versus hybrid quantum classical. And yeah, so what challenges we have when programming quantum computers? We have challenges to choose a real world problem which is suitable for quantum computer, because not all problems are suitable for quantum computers. Some problems are simply will never be executed on quantum computer because digital computer can do that better and faster. Then, and also we need to choose real world problems, something that solves real world problem, not some abstract problem which is not of use. Then we need to choose an existing, to choose which quantum algorithm we will use. Will we use existing quantum algorithm, or we will develop a new quantum algorithm? Then we need to efficiently encode data into quantum state, which I mentioned already, efficiently compile quantum program for the target quantum processing unit. What means compile? Means split program into instruction sets. So split our set of matrices that we want to execute, split into instruction set of matrices that quantum computer can execute. And then we need to efficiently decode data from the quantum state, and we need to deal with noise, because quantum computer simply has noise. We are not able to very precisely control quantum effects. So we have noise. So we need to somehow do noise correction, noise suppression, mitigation, and so on. And this is it was end of part 2. Now let's see, do you have questions? I see some, let me try to. Okay, so one participant asked, Abdul asked why we don't use imaginary part in 3-qubit model. We use only in my example, I didn't put imaginary part. So let me, in these examples, I somehow forgot to put, actually we have, for example, in this example, there is imaginary part. But yes, we can have both imaginary and real part in quantum state. It's 30 minutes from now to the end. Okay, what is the number? Let's see which parameter. Don't know which parameter anyway. Okay. How close are we to the end? Let's see how much time I have. So presentation ends in 5:15, I think. And we are now 15 minutes to the end. Okay, I will try to make it in 15 minutes. Let's do it. Let's go to the part 3, hands-on. So idea was, but I don't think I will make it everything in 15 minutes. So let's see. I want to show you simplest encoding scheme, which is binary encoding, how to encode binary numbers into quantum state. This is relatively simple. This because more complicated encoding will take more time to explain. Then I will show you how to make quantum program for almost any function. I have some trick to show you for small functions that have small input and small output. By using binary encoding, you can make quantum program for any function. And we have tool which can automate that. We at Quantastica, we have tool for that. This is one thing. And second thing is exercise. I will make program for factoring small integers without using famous Shor's algorithm. I will make algorithm on the fly, and it is not Shor's algorithm. But I don't think I will get. I have prepared the Jupyter notebook and everything, but I don't think we will do it in 10 minutes or 15 minutes. But let's go. Let's see how far we can get. Binary encoding. Let's say that you have number one single number, and in this example number 5, and you want to encode number 5 into quantum state. By using binary encoding, you need 3 qubits because number 5 is, when written binary, it has 3 digits. So this is 3-digit number, and to encode it into quantum state, you need 3 qubits. Of course, by using different encoding schemes, you need less qubits, but only for binary encoding, you need as many qubits, as many bits. So this is binary encoding. And to encode that, it's very easy actually, because so this is our 0 state or initial state. Quantum computer is in state or all 3 qubits 0 with 100% probability. And what we do, we put it into state into which it has 101, which is our number 5, 101, decimal 5, binary 101, with 100% probability. So this is what we do. And to do that, there is a gate or matrix named X. So this is Pauli X gate. And here you can see that matrix and tensor product of that. So if you have 1, then you have X gate. When you have 0, you have identity gate. And again, we have 1. So we again have X gate. And by multiplying those 3 gates, those 3 matrices, tensor product of those 3 matrices, you get the matrix which will transform your 0 state into state in which this outcome will have the maximal probability. So this is how you binary encode number into quantum state. Relatively easy. In quantum program, you will execute two gates. You will execute gate X and on qubit 0 and X on qubit 2. So this is how you do it. Now, but you can also encode multiple numbers. For example, let's have three numbers, 1, 4, and 5. So this is binary representation of 1, binary representation of 4, and binary representation of 5. Now, how we do that? We put state into probability of 33.33% probability of number 1, then 33% probability number 4, and 33% probability of number 5. This is how we can encode multiple numbers. And actually, we have encode 8 numbers. Into 3 qubits, we can encode 8 numbers. This is binary encoding. And now, this way, we can convert any truth table into set of vectors, into set of quantum vectors. So why I'm doing that? Because I want to show you how to convert any classical function into quantum program if input and output is small. If it's only few bits, then you can do that automatically. And in order to perform that, you need to first to build truth table for your function. Then from input, so we have input and output. And in this example, this is NAND gate. This is AND and inverse at the end. So binary function, and it has two inputs and one output. And okay, so this is truth table. When we have 2 1s at input, we will get 0 at output, and in all other cases, whatever is input, then we will have 1 as output. This is NAND gate. And how do we do that? We split that into input, and we encode input in one set of vectors and output into another set of vectors. Let's see. So this first row, this 0, 0, this first row, 0, 0, we encode that into vector, which is also 0 state, 0, 0 element. 0 element is 1. All other elements are 0. Now 0, 1. So this is element 0, 1 is 1. And so on. And 1, 1, this is element, this is 3 decimal. And so element 0, 1, 2, 3 is 1. This is how we encode each of these possible inputs into vectors. And output, the same with output. So we have 1 as output, we have 1, so 0, 0, 1. Now, problem is that because we have the output is not unique. Output is not unique. And then we will not be able to make unitary matrix. The transformation will not be unitary. And for that reason, we need to add as many bits as to make our output unique. And now we have 0, 0, 1. So actually, we have only 1 as 1 bit at output, but we need to add 2 more bits because we have three equal outputs. And to make it unique, to make this row unique, we add bit here. For example, we have 0, 0, 1, 0, 1, 0, and 1, 0, 1. So these 2 additional bits are only bits which we need to make output unique, and then we encode them. We encode them into this into vectors. And now we have 2 sets of vectors. We have input vectors, and for each input vector, we have output vector for entire truth table. And now we need to reverse engineer quantum circuit out of it. So we have input vectors, and we have output vectors, which we do in this previous step. And now question is, which unitary matrix, so which is common multiplier, which matrix will by multiplying, for example, this vector with that matrix will give us corresponding output vector. And the same matrix which will second input vector transform into second output vector. So we are searching for common multiplier unitary matrix. And then when we get the matrix, we can decompose it into quantum circuit. And for this, we have tool. So we at Fantastica, we have tool. So you provide your input and output vectors, and then it will give you quantum program. And this is how we, by using binary encoding, how you can make quantum program. Of course, this is not very useful. Why? Because in order to make quantum program, you need to, in advance, to know both input and output. So if you know what is output, then why do you need a program at all? Then the question, I can answer that question because we can do automatical scaling of quantum algorithms. This is something that we also in Fantastica do. So we generate small problem, we generate input vectors and output vectors for small problem. Then we make unitary matrix or directly quantum circuit which solves that small problem. And then we have tools by using machine learning tools which scale that problem to size for which we don't know what is the what is input and what is output to the scale in which we don't have. I mean, we didn't provide examples. We didn't provide examples, but we get circuits which can calculate bigger size problem of bigger size. This is our approach. This is how we make quantum programs, and this is why we need why we create program. But we already have output, you know. So why create program if we have output? Let me see what is the time. Okay, we have 7 minutes only. The same we can do with reverse. If input, so this is the same thing, the same truth table, but inverse. We have output, and we are interested in what is input. So if we have 1 at input, so what could be output? And the answer is we for each unique input we have only 1 vector. In this case, we have 3 unique inputs. For 3 unique inputs, we need only 1 input vector. This is second unique input. We have another vector. So this is 1, and this is 0, encoded into state vector. Then for each output, which we merged into same, into same input, each output with same input, we make vector with equal probability of these outputs. So for first input of 1, we have 0, 0. So 0, 0 element is 33% probability. This number squared is 33, 0.33. And the same for each. So 0, 1 and 1, 0. So this is how we encode. And then when we execute program and quantum program, and when we have 1 at input, it will give us 0, 0, 33% probability, 0, 1, 33%, and 1, 0, 33%. This will be our result. So quantum computer will tell us that if input into NAND is 1, then if output from NAND is 1, then input could be one of these 3 numbers. I mean, one of these 3 combinations of A and B. This is the same thing, but opposite in opposite direction. And now it's time to code. Let's see. Time to code. I prepared Jupyter notebook. I have some utility functions at the beginning, which I will not bother you to show. Let's see. So this is example 1. This is this NAND example. where I made truth table for NAND gate, and I will execute it, and we have truth table. From truth table, we generate vectors, input vectors and output vectors, and then we reverse engineer circuit from vectors by executing by using our Quantastica tool. So it's circuit from vectors for pairs. So for these pairs of vectors, when I execute, it takes a few seconds and it gives us the circuit. So this is quantum programmed for this truth table. It can be, by the way, simpler, much simpler. We can do it with only 2 gates, but if we change order of bits here, I mean order of which qubit is which bit. But anyway, so we have a quantum program, and then let's run the program. So I made this quantum NAND program, which takes A and B, which takes 2 bits at input. We create quantum circuit. We encode input into by executing these X gates, which I explained earlier, and then it appends the main program, which we get this program, which we get from automatically by reverse engineering, and then it executes the program and decodes the output. And let's see. So I will execute this. Now, because input is 1 and 1, so we have 1 X gate at 1. If this is 0 and 0, and then we will not have, when this is 0 and 0, we don't have X gate. When it is 1 here, we will have X gate. When this is 1, we will have another X gate. So for 1, 1, result is 0. So we measure 0 from quantum computer. And when we have both 0 or 0, 1, again, we'll measure 1. We have both 0, it will measure 1, and so on. So it works. And now in the exactly same way, I made factoring program. So first of all, I generate truth table from let me show you how. So this is data. 0 is equal to 0 times 0, and so on. So 6 is equal to 3 times 2. So just multiplication, just a simple multiplication. From that data, we build truth table. We have 3 bits at input because number 6. So this goes up to 6. So this is a very small factoring program. So it can factor numbers up to 6. So because 6 requires 3 bits, so we have 3 bits at input, and 2 bits for one factor and 2 bits for another factor, because factors goes up to 3. So we need only 2 bits. And this is how truth table looks. And then from that truth table, we generate vectors. I will execute that. And yes, it generates vectors. And now we reverse engineer quantum circuit from vectors. So we call that circuit from vectors and provide these vector pairs. We have some strategy here and so on. And when I execute, it takes few seconds, let's say 10, maybe 15 seconds. I'm very close to the end. I know that I approached the end of time. Okay. So this is the circuit which performs factorization. And then let's run the circuit. So quantum factoring, input is n, number n, which we want to factor. We create quantum circuit, add some registers into it, quantum register, classical register. We encode input, so we convert that number to binary, encode that by applying X gates into circuit. Then we append main program, which is this program returned automatically from our tool. And then we measure output and decode output and print that to user. And now let's execute that. And let's say, so let's factor number, which number? Okay, let's factor number 6. So quantum factoring 6, it will give us 3 times 2 with probability 48.93. Like it should be 50% probability in the ideal case, but you know, because noise, we will have different probability. So 3 times 2 and 2 times 3 is 6. Or if we factor, for example, number 4, it will tell us that it's 2 times 2 with 100% probability. And then we can factor, for example, number 0. What happens when we factor number 0? It's 1 times 0, 0 times 1, you know. So we have with relatively equal probability. So yes, so this program is very simple quantum factoring, which we made by binary encoding input. And just to say 2 things, and I'm finished. So using this method, in order to make program, we need to know result in advance. So what is the point? So point is that for some algorithms and for some problems, we are able, by using our machine learning tools, to grow, to scale up this circuit, to scale up to bigger size, for which we didn't provide output. So we don't necessarily need to have output. We need only small version of it, and then we could scale up. Then what is binary encoding pros and cons? So this is inefficient. It's waste of space, because for one binary number, we are using one element of entire state vector, which can be giant. And this is waste of space. But from other side, it's easy to encode. It requires only small number of shots, so small number of executions. So it's relatively easy to get the most probable element from it. We don't need to execute billion times. We executed 100, or depending, I mean, how many qubits we have, but small number of shots, and it's easy to measure and decode. So it has pros and cons, but you know, usually quantum programs are not using binary encoding both on input and on output. On output, they use, for example, Shor algorithm will give you binary output, but input is not binary. I mean, it's very rare that quantum computers use both binary input and output, but this is only to show you, or this is only for simplicity to give you idea how to program quantum computer. And this is the end of my presentation, and it's time for questions and answers, or ask me anything. I will stop sharing.
So we're over time. So I think we can take questions. I'm so sorry for that.
Let's see, there are some in chat messages. Maybe I can read from chat. There is one question in Q&A window, which says, when the photon is in superposition state, not vertical or horizontal, what we can read? We can read one of those 2 states. We can read vertical, or next time when we, next photon, because when we measure photon and we measure vertical, it will stay vertical. It lose superposition. Measuring destroys superposition. So we will read one of those 2 states. This is the answer to that question. Let's see others. Hello, Petar. What is the number?
Mr. Peter, can you hear me?
Yes, I can hear you.
Okay, so we're over the time. So I think we can take questions, and we should end the tutorial now. We have the other one in 5 minutes.
Yes, I understand. No problem. Thank you. I'm sorry for extending time, for overtime. And I hope that this presentation was interesting and that people are satisfied with my presentation. And I'm happy if you can contact me anyway. I'm happy to answer your question. You have my email maybe or something. I'm happy to answer.
Okay. Thank you, Peter. It was very interesting actually, and thank you everyone for attending the tutorial. We will have a short break now and see you back here at 5:30. Thank you.
Thank you. Have a nice day. Bye-bye.